Welcome to section 1.1, our first section. We're going to talk about systems of linear equations. So this probably will relate to classes you've already done before, and they'll tie in and give us a new perspective. So we're going to talk about what are systems of linear equations, what are matrices, and do some examples of how to solve them. So first off, let's talk about systems of linear equations. What are they? Well, a linear equation is an equation with variables x1 through xn. This is instead of the different x, y, z, etc., because we could have as many variables as we want. Notice each variable, so the subscripts are just labels, and there's no superscripts, there's no exponents. So these are all linear components that we have to deal with along this process. Now, b and all the coefficients are constants. They can be real, they can be complex. In our class, we're going to focus on real numbers, but they could very well be complex. So a system simply means one or more such equations. An example would be this, and notice I spaced them out so all the x1s are all lined up and x2s and x3s. So this is an example of a system with 3 equations and 3 variables. All right, so what are all the different possible solutions? Well, this should take you back a little bit to algebra. You have 3 different solutions that we can come up with, but a solution in general is a list, S1, S2 through Sn, of numbers that satisfy it. Now notice the order of these is important. So you can't just say the answer is 3. Well, that doesn't make sense. We're identifying what the variables are. So often this looks similar to what you think of a point. You can think of it as an ordered pair or set. Now, a solution set is all of the possible solutions. And the reason that's important is because it's possible we could have more than a single solution. In fact, 2 linear systems are considered equivalent. They have the exact same solution set. So they may look different, but if they have the exact same solution set, then they are equivalent. So possible solutions include no solution. So it is possible that a system has no solution at all. It's possible it has exactly one unique solution, or it's possible it has infinitely many. So those are your 3 options. Please do not say that there are 2 solutions, because if there's 2, then there's infinitely many. And this will make more sense as we get further and further on. Now, a system of linear equations is considered consistent if it has 1 or infinitely many, meaning it has at least 1 solution, and inconsistent if it has no solution. So these are another terms that we use, consistent or inconsistent. Consistent means I can solve it. Inconsistent means I cannot solve it. Now, why is this all important in terms of linear algebra? Well, we're going to use something called a matrix. Now, a matrix is a rectangular array. So all of you computer science people, you probably heard the phrase an array, which is an ordered columns and rows. And the values that we are going to have are going to be real or complex. The truth is, matrices, the plural of a matrix, can include anything. They can be words, they can be functions, they can be all sorts of different options out there. So we in this class are going to focus on real matrices, but they hypothetically could include a lot of different options. And linear algebra actually goes into those. Now, examples of matrices are the ones that I've just given, where the example A and example B are 2 different matrices. Now notice, example A has 3 rows and 3 columns, where B has 2 rows and 3 columns. And this relates to how we refer to the size of a matrix. A matrix is M by N, where M is the number of rows and N is the number of columns. So rows always comes first, columns second. So A is 3 by 3, and B is what? How would you define B? Hopefully you thought about that for a second and said it's 2 by 3. Using this, we then can talk about a specific element in the matrix using Aij, where I is the row and J is the column. Similar to how we have rows and then columns in terms of the size of a matrix, Aij tells us the element in row I and column J. So for example, A23, I would come up to matrix A. Notice the difference between uppercase and lowercase, by the way. That's very specific, and the common notation in linear algebra is that capital letters are for the matrices and lowercase letters are for the individual elements in the matrix. So A23 would say I go to row 2. So that's going to be, let me just highlight that for you. So that would be this row, and 3 tells me I come to column 3. And notice where they overlap. Well, they overlap at that 1. So our answer is 1. Similarly, A32, well, A32 is, we do row 3 and column 2, and notice the overlap with the 0. So the answer is 0. Now, you could have guessed that because, well, row 3 has all zeros, so anything works in there. But this is an important thing as we go a little further on and talk about different things. So these notations are kind of critical for you to fully understand it. All right, I'm going to pause the video here, come back and watch the next video as I explain how we can use these to solve systems of equations.